Okay. All right, get out the worksheet that I gave you at the end of class last time. It says numerical, it says 3.6 numerical derivatives. And I put the table up there on the overhead, but you can also just look at the table on the paper if you want to. Yes, sir, go ahead.
Wait, so whatever is, when it's asking for the derivative, are you plugging whatever the number is in the parentheses into that?
Yes, that is exactly accurate. If I told you that f of x is equal to x to the third power plus 3x squared, okay? And then I asked you, well, what is f prime of 2? If I asked you what is f prime of 2, well, what you would do is you would find f prime of x first. So f prime of x is 3x squared plus 6x. And then you would plug 2 in. So f prime of 2 would be 3 times 2 squared plus 6 times 2, which would be for 12 plus, which would be 24. Did that make sense? Okay. So anytime you are asked what is, g prime of 5, that means that you are plugging 5 into the derivative. It's also, do you know what this tells you? Do you know what this means? What does this 24 mean? It is the rate of change in what? At x equals 2, but the rate of change in what? Well, slope is rate of change. The rate of change in the original function, the rate of change in f of x. So f of x has this function has a slope of 24 at x equals 2. Okay? Is everybody making the connection? That is a very important connection in calculus, that you understand that the plug-in value into a derivative gives you the slope of the original function at that plug-in value. Okay? Now, the y value is going to be f of 2, which is 8 plus 12, 20. So at the point 220, it has a slope of 24. And the equation of the line tangent to f of x at x equals 2 is y minus 20 equals 24 times x minus 2. Yes?
I know this isn't like totally related, but it has to do
Sure.
with this. For a normal line, do you just make the slope negative? Please say it.
Negative reciprocal.
Oh, I put reciprocal. I didn't put negative.
I didn't do reciprocal. I just did negative.
And you do concede that we did do a whole quiz on it, right? Okay, just checking. Now, I'm not throwing that at you. I'm just making sure that we're aware that degradation of knowledge is a very dangerous thing in AP Calculus, because this is a snowball. As you learn something, it is expected that your knowledge in that will stick. Okay, in as much as working your way through 12 years of math, previous knowledge is expected to stick. Now, we are realistic, and we understand that the knowledge does not stick. Okay? But that is not the fault nor the responsibility of the teacher. That is on the student. So when something doesn't stick, when you don't remember something, you have to go back and review it. So the equation of bringing up the normal line now, so the normal line of this now would be y minus 20, the equation of the line normal to the graph of f of x at x equals 2 is y minus 20 equals negative 1/24 times x minus 2. Okay. Well, that's why the quizzes are there, to remind you. Right. But when you get reminded 3 times over a few weeks, okay, eventually it's going to stick. You're not going to forget. There are things that you're not going to forget. What's that? Good, excellent. Yeah. I will also say this. Do you know what I have noticed? I think maybe out of my 40-something AP Calc students, I think 3 of them, maybe 3 of them, are still unsure about whether to determine whether an object is speeding up or slowing down?
That was the easiest.
Okay, right, but I have asked that question so many times now, it is sticking. Okay, and a lot of people won't even remember that, like in other AP Calc classes, may not even remember that in April. Okay, but you guys are not going to forget how to identify whether an object is speeding up or slowing down. Okay, good, excellent, because that is one of the important pieces of knowledge in AP Calc. Okay, all right. Yeah, I'll probably keep asking that one until I have another application. There is a fire engine outside. Don't get up. There's a fire engine outside. No, we're good. We're good.
I don't know.
Okay.
The fire alarms aren't working today.
No, I don't know what it is. Maybe it's just a visit from a friendly neighborhood firefighter for fun.
Their sirens on.
Yeah, okay, all right.
And they're holding
I got you. I got
Oh
you.
my God, they're getting the fire hose off.
No, they're not. All right.
Mr. Ryan was like, oh, God.
Yeah. All right. Let's look at this table here. Okay, so what you see underneath the table are definitions for functions. Okay, so it's telling us that the function m of x is the product of f of x and g of x. R of x is the product of g and k. P of x is the quotient of h and j. T of x is the quotient of f and h. Q and w are both composition functions. Q of x is j of k of x, and w is f of g of x. All right? So given that, we are now going to look at a couple of these problems. Let's look at number 4. It says, what is r prime of 2? Okay. Now, r of x, what is r of x? G times k, right? So if we want the derivative of r of x, what is r prime of x going to be equal to? Yeah, the derivative of g, so g prime times k plus g times k prime. Is this correct?
Wait, where's K at?
Product rule? It's in the table.
Oh, at the bottom.
There's values in the table. Yep. And so if we want r prime of 2, that's going to be g prime of 2 times k of 2 plus g of 2 times k prime of 2. And all of those values are in the table. So what's g prime of 2?
1.
It's 1. Okay, so that's 1 times, what's k of 2? 3 plus, what's g of 2? Negative 4. And what is k prime of 2? 2. So now it's just 1 times 3 is 3 plus negative 8, negative 5. Okay? And now, I know that the question does not ask this, but what if the question did ask, what is the equation of the line tangent to r at x equals 2? Okay, well, negative 5 is the, what piece is that? That's the slope.
So y.
We need the y value. How are we going to get the y value?
Plug it in the original.
Plug 2 in the original. We need r of 2, which would be g of 2 times k of 2. And what's g of 2 is negative 4. And k of 2 is 3. So it's negative 12. And so what would the equation of the line tangent? Y plus 12 equals negative 5.
Did you say normal or tangent?
I said tangent.
Okay, and 5 times x minus 2.
X minus 2. There we go. Isn't it amazing just with a table of values that we can answer so many questions? I don't know if you think that's amazing. I think it's pretty amazing. Yeah.
What is x and y equals mx plus b?
That's a form. This is okay. Y equals mx plus b is a form of a line. This is the slope intercept form.
Okay, what's B?
B is the y-intercept.
Okay, good.
Yeah. Okay? Because if the slope is 0, 0 times x is 0, right? And y, that would be a horizontal line at B, which would be the y-intercept. Okay? What we have been writing here is called point-slope form. Point-slope form. Okay? Yes, sir?
The x minus 2, the 2 is coming from R.
Yes, from the R of 2. That is the x value that we have plugged in. The y value that we get from that x value is negative 12, so y minus negative 12 is y plus 12. The slope we got from it is negative 5, so there's negative 5. And then, of course, if we wanted the normal line, we would just change this to positive 1/5. Okay? All right. All right, let's now look at, let's do number 11. 11. Oz go up to 11. I'm sorry, I can't not say it whenever I say the number 11. I'm really sorry. Did I already explain 42 to you? Hitchhiker's Guide to the Galaxy? No, but forget it. We'll do it another time. All right, number 11. Yeah, too many times. Listen, you have to see it. You got to see This Is Spinal Tap. It is a spoof on a documentary of a rock band, and it's extraordinarily funny. T prime of negative 1.
You watch Key and Peele?
I don't watch much anymore. A lot of my jokes come from movies of days past.
You should watch Key and Peele.
Okay, so what would I need to be able to find the derivative of t at negative 1? The quotient rule. Why do you say that? Yeah, this is t of x. T of x is equal to f of x over h of x. Okay? So what is t prime of x going to be equal to? Right? Derivative of the top.
Oh.
That's right. Times the bottom. Okay, now listen. A lot of people are still messing up the quotient rule. If you just got your quiz back from, well, no, it's a lot of people. I would say half of my students. Half of my students, do you know what they're doing for the quotient rule?
I just did the derivative.
Yeah, they are doing exactly what I said to not do. Am I right? What was when I taught you before I actually taught you the quotient rule, what did I tell you is not the quotient rule? I said it is not the derivative of the top divided by the derivative of the bottom. Right? Okay, many people are still doing that. Like half of my students are still doing it.
Oh, no, I'm not saying
Every quiz.
Oh, okay. You actually did really good. I really like the way that you recovered points without knowing what the derivative of some of the trig functions were. That was very creative.
What did you do?
He wrote, look at this, for the quotient rule, he wrote 3t squared times whatever. Oh yeah, he put in g, and over here he put g equals d dx of cosine of t. And I was like, wow, that's really creative. I'll give him the points for that.
Points taken off because I didn't put the right.
You put them in the wrong order. Yeah. It was really creative. A good way to recover points. Yeah. I don't think so. Where?
V is on the bottom.
Okay. Yeah, but does it say v du? All right, I'm going to page. Rules for differentiation. I'm going to page 120. Page 120. Yes. Look, let me show you what it says. Okay. This is what the quotient rule says in the book. Guys, watch this. It says d dx of u over v. d dx of u over v. This is what the book says. And u is a function of x, and v is a function of x. Okay, so d dx of u over v. This is what it says. It says v du dx minus u dv dx. I can appreciate that the v is written first, but which derivative is first? The top or the bottom? Right, so even though they wrote v, okay, now, are you saying that when we do t, what is it, t equals what, f over h?
Yep.
F over h. Are you saying that t prime should be h times f prime?
No. That would be like H prime.
Yeah, look at this. Which derivative is first? The top or the bottom? Du dx is a derivative. V is not a derivative. This is the derivative of the top times the bottom. They just happen to write them. Remember, with multiplication, it's okay to swap them. This is what they're saying. The way I taught you was derivative of the top times the bottom, minus the top times the derivative of the bottom, right? This is what they're saying. They're saying the bottom times the derivative of the top. Well, the bottom times the derivative of the top is the same thing as the derivative of the top times the bottom. Yeah. Okay. So make sure that regardless of which one, whether you write the derivative of the top or the bottom by itself first, know that in the very first term of the derivative and in the quotient rule, it is always includes the derivative of the top. The second term after the minus sign includes the derivative of the bottom. So what we're going to have here for t prime, so t prime of x is going to be the derivative of the top, which is f prime of x, times the bottom, which is h of x, minus the top, f of x, times h prime, the derivative of the bottom, all over h of x squared. Right? So, what is f prime of 2, or of negative 1? Sorry, what's f prime of negative 1? Is it 9? Okay, f prime negative 1 is 9. 9 times, what's h of negative 1?
Negative 1.
Negative 1?
Yes.
Okay. Minus, what's f of negative 1? 1. And what's h prime of negative 1? 4. All over, h of negative 1 is negative 1. Negative 1 squared. Right? So, negative 9 minus 4 over 1. That's negative 13. Okay?
Which one was that for?
That was number 11. 11. Somebody should go, when I post this on YouTube, somebody should go in and they should post a link to the clip from This is Spinal Tap. I'm sure somebody put a clip of this on YouTube. Yeah, you're going to do it? There you go. All right, so let's now try it's called This is Spinal Tap. The whole title of the spoof is This is Spinal Tap. Let's go to number 15, Q prime of 2. 11. Yeah, and you're looking for our amps go up to 11.
I'm just gonna.
I might not study math, but I'll know that one.
Maybe he'll get credit. It's getting really hot.
All right, number 15, Q prime of 2. 15. All right, now, Q of x. What is Q of x equal to? J of k of x. It's a composition function. Okay? So if we want to know what Q prime of x is, what is Q prime of x going to be equal to? Yes, k prime. Derivative of the inside, k prime of x, times j prime of k of x. Okay? J prime of k of x. Yes. Yes. That is exactly right. That is exactly, I mean, not even part, that it was, remember the other day when I like overrode your definition with my definition? Well, I'm not doing, that was perfect. What you just said was better than anything I could have said. Okay? You are going to find, you're going to find out what k of x is and then plug it in for j prime of x. J prime, okay? All right, so here, if we want q prime of 2 then we want k prime of 2 times j prime of k of 2. And what is k of 2? I don't think so. Oh, you were looking at negative, I think, yeah. It's 3. If you go down the column of 2 and go down to k of x, k of 2 equals 3. And therefore, what we want here is we want k prime of 2 times j prime of 3. J prime of 3, you're saying it's 8? That sounds right. And what is k prime of 2? I think it's 2. You're looking at k of 2. K prime of 2 is 2, and j prime of 3 is 8. So what we've got here is 2 times 8, so the answer is 16.
That's not a very big number at all.
Okay, I don't think so. Can you solve that?
Yeah.
You can?
I used to change the
You're the second person that I know of. I had a student last year, and I also had him in class the year before. He could solve, I could do whatever I wanted with the Rubik's Cube, and he could solve it within, I think, a few minutes or 5 minutes or something.
5 minutes, he's phony.
I don't know. He wasn't. Listen, I don't remember how long it was. It could have been a minute. I can't remember. But he would solve it every single time. Yeah, no. It was in less than 5 minutes. So, yeah. But it was also a terrible. It was a junk Rubik's Cube. It was like a dollar store Rubik's Cube. Yeah. So it didn't turn very smoothly. Yeah. Oh, that's pretty funny. Okay. All right. So do we have a good idea on how to do these numerical problems? This worksheet, well, the one we just did 3 problems for, the answer key for that worksheet is online on my website right next to the download for this worksheet, which I think is like day 25.
It's on the back.
What's that?
It's on the back.
What's on the back? I didn't put it on the back. Okay, so you can work on them, and then look up the answers to see how. Yeah, people who know how to do it know how to do it. People who don't know how to do it don't know how to do it. Yeah, I used to pop it apart and slide it back together, and then.
Oh, I can go.
You did, yeah. Of course. Why not? Okay, now let's do one more problem, one more chain rule problem from the textbook. We're going to go to page, chain rule. Yeah, we're going to go to page 154, question number 59. Yes, sir.
Is the quiz on Friday like a harder version of the chain rule?
No. What you have seen so far is about what I can do. What I'll probably do is, I haven't given you a geometry question yet. I'll probably put a geometry question.
So it is
I will.
Yeah,
Friday is chain rule. I'll probably put a geometry question on there, and I will probably do primarily numerical and graphical, because we did analytical today, right? So I will probably do primarily numerical and graphical on Friday. So if you can do that stuff that we just did, if you can do that whole worksheet,
is this basic?
then you should be able, and then apply it. Like I might give you information like that, only instead of giving you F, G, and K, and J, I may actually give you X of T, V of T, and A of T. I may give you, I might give you a table with motion values, and then ask you if an object is speeding up or slowing down, when, given that its velocity is. This is sort of confusing. Okay. There's a couple things I can do. I can tell you that the table values are the motion of object A, and that the velocity of object B is twice the, is V of 2t. I guess you could say, now making it a chain rule problem. Okay? Or I can give you table values that are f of x, and g of x, and I can tell you that, that the velocity is equal to f of g of x, or f of g of t, I guess you could say, and then you have to calculate the velocity at a particular value, and then you have to tell me if it's speeding up or slowing down. The velocity could be a particular value, and I might ask you, what is the speed of the object, in which case you would give me the absolute value of whatever the velocity is. I may ask you what the acceleration is or something like that. Okay? All of this, everything in calculus, it weaves together into a single body of knowledge. Okay? All right.
That's for Friday?
For Friday, yeah.
Our economics are.
That's going to when we do optimization, we are going to retake the economics quiz when we do optimization, which is section 4.3, I believe. Okay, number 59 on page 154, orthogonal curves. All right, two curves are said to cross at right angles if their tangents are perpendicular at the crossing point. An image of this would be something like this. Let's say that you have a curve that does this, and then let's say you have another curve that does this, okay? And the tangent, the line tangent at this point to this curve looks like this, and the tangent to this curve looks like this, and they cross at right angles. So at that point, these two curves are orthogonal. Orthogonal. It says two curves are said to cross at right angles if their tangents are perpendicular at the crossing point. The technical word for crossing at right angles is orthogonal. Okay, so these two curves are orthogonal at this point.
Oh, that's exactly what I was thinking of in my head.
It-
I was about to say that.
Really? This? Okay, good, because that's what it is. You have a curve, you have two curves, and they're one of them. So how would this happen? If the slope of this one right here is 2, what is the slope of this one?
It'd have to be negative.
Yes, negative, not negative 2.
The neighbor just slope by itself.
Oh, negative. It's the tangent.
Yeah, what did you say?
Negative 1/2.
What just flipped? Oh, the page flipped. Sorry about that. Thank you.
Negative 1/2.
Negative 1/2. That's right. Remember? It's going to do it again. I can see it. It's happening. Here. Okay. All right. Yeah, it's gravity. Yeah, what did we say? The negative?
1/2.
Yeah, negative 1/2. Guys, wouldn't orthogonal, it would be one of them would be normal to the other, right?
Yeah.
Or each one is normal to the other. That's basically another way of saying that this curve is normal to this curve, and this curve is normal to this curve at a particular point. But the technical term for it is that these two curves at that point are orthogonal. Okay? Show that the curves y equals sine of 2x, and y equals negative sine of x over 2 are orthogonal at the origin. What does origin mean? 0, 0. Okay, so at the point 0, 0, we got y equals sine of 2x, and then we have y equals negative sine of x over 2, which instead of x over 2, I'm going to say 1/2 x. Is that okay? Just easier to recognize as slope and x. Okay? Slope of, this is a linear term here, right? And so, how would we determine whether these two curves are orthogonal? What do we need to know about these two curves? We need their slopes, correct? We need their slopes at the point 0, 0. This passes through the point 0, 0 because sine of 0 is 0. This passes through the origin because negative sine of 0 is 0. So now we just got to find out what their slopes are at 0, 0. Which we need, so that we need the derivative. So the y prime equals, derivative of the inside is 2 times cosine of 2x. There we go. Right? And if we plug 0 in, if we get y prime of 0, if we plug 0 in, what's 2 times 0? What's cosine of 0? And 2 times 1? 2. What's the derivative here, y prime? It's negative.
Negative matter?
Yes, well, it matters in the sense that, why don't we ignore the negative for a second and just whatever the answer is, we'll make it negative. But the derivative of sine is cosine, right?
So it's
Okay?
negative?
So negative cosine, but what's the derivative of the inside? 1/2. So it's actually negative 1/2 cosine of 1/2 x. Okay. And then what's 1/2 of 0? And what's cosine of 0? 1. And what's 1 times 1/2? And if it's negative, y prime of 0 is negative 1/2. Are they orthogonal?
Yes.
They sure are. Look at that, negative reciprocal slope. Yep. Very good. Okay. So that, you know, you look at number 59, you're like, oh my gosh, here's this crazy word problem. Not that hard, right? Okay. All right.
Mr. Ryan is standing in front of you.
Come on. You can be Mr. Ryan. Yeah.
No.
Yes, you can, huh?
I think not.
Number
It's
6.
still a little bit too early in my life.
All right.
Said no man ever.
Said no man ever. Yes, you can. And by the way, you don't really want to be Mr. Ryan. You want to be you with my ability in AP Calculus. Actually, you want to be better than me. You want to be better than me because my ability in calculus is very narrow. It's not even that good. All right, number 6 says y equals 5 cotangent of 2 over x. Y equals cotangent of 2 over x. Okay, now, is it okay if we do it our way instead of with u substitution, or do you really want to do it with u substitution? You want to do it our way? Okay. Can I say that this is cotangent of 2x to the negative 1 power?
Yep, that'll work.
Is that okay? We just know that we cannot plug in 0. 0 is not a valid input for this, correct? Because we can't do 2 over 0. So it's this where x cannot equal 0. Okay? What did I forget? Oh, the 5. There was a 5 in there, wasn't there? Sorry. 5,
Okay.
5. There we go. Okay. Yes.
So is the 5 is the 5 a constant? Like
Yes.
do I multiply that by?
Yeah, the 5 is a constant. If it's not 5x, you really got to get used to this. Anytime you have a constant attached to a function, when you start to do derivatives and such, you can just remove the constant temporarily and bring it back in.
Are you serious? So that means, so does it count?
Well, when you bring it back in to calculate, it does
I mean,
count.
So you don't have to find
You don't have to do the derivative. If we, yeah, it would be 0. If we did the derivative of this with the product rule, we would do 0 times whatever this is, which would 0 it out, and then it wouldn't be there anymore.
So if I put like both answers, like I put like
If you do the product rule correctly, it would still be the correct answer.
No, but I mean I put 2 answers because I didn't know which one was right.
We'll see. You know what they call that? On the AP exam, if you do 2 separate solutions that are different, here's what they will do. They will grade the first solution, assign points. Then they will grade the second solution and assign points. Then they will add the points together, divide by 2, and round down. So if you get 0 points on the first solution and 5 points on the second solution, they will add 5 plus 0, divide by 2, which is 2.5, round down, you get 2 points total for your... Yeah.
Was it worth it?
Now, if you know your first solution was wrong and you put a big fat X over it, they will not grade it. And now you get your 5 points.
Big fat X.
Okay? Don't bother erasing. Don't even bring an eraser. Don't even bring an eraser to the AP exam. Just cross it out. Anything you do, if you don't like it, cross it out.
What's wrong with you?
Yeah. It takes time.
It's too long.
Yes.
So like on the quiz when it was like 4 cosine or something, you just keep the 4 there, or I don't remember.
You just leave it there. That's correct. Yep. All right, so here we go. We're going to do the derivative of this. We're going to do the derivative of the inside first.
You're lying.
Well, okay, you want to do the derivative of the outside first? I'm okay with that.
No. You're supposed to leave the 5 there?
Yes.
Oh my God.
It's a constant multiply. We learned it in section 3.1. Section 3.1. 3.1. Properties. That's notation. Oh, maybe it's not 3.1. Hang on. I'm going to find it. Differentiability is 3.2. Let's go to 3.3.
We learned it somewhere.
Yes, somewhere. I remember doing it. Properties of derivatives. That if f of x equals 5 times g of x, then f prime of x equals 5 times g prime of x. Okay? Constant multipliers. Weren't they the same way back in limits? If we had a constant multiplier, it stayed the same? Yeah. Remember we said that that if the limit as x approaches a of 5 times f of x is equal to 5 times the limit as x approaches a of f of x. Constant multipliers. Pretty much in all of calculus. And I'll tell you if we ever find a case where it doesn't work, and there'll be a really good explanation for it. But generally speaking, constant multipliers, you can always put them on the outside. Always. So now, here, this 5, we're just going to set the 5 aside for a minute and do the rest of the derivative here. So, the derivative of the inside, 2x to the negative 1, is negative 2x to the negative 2 power. You with me, Bianca?
Yes.
Okay. Which is the equivalent of negative 2 over x squared. Negative exponent goes to the bottom. Negative 2 does not have a negative exponent, so it stays in the top. So negative 2 over, and if we now multiply that times the 5 times negative 2 over x squared is negative 10 over x squared. No, you can leave it as 5 times. I mean, it's not, if it was a multiple choice test,
Right.
They wouldn't do this, and you'd be harder finding your answer. But it's 5 times negative 2 over x squared. So that's the derivative of the outside, inside, times the derivative of the outside. What's the derivative of cotangent?
Sine. Negative sine.
No, this is not cosine, this is cotangent. Cosecant squared. Negative cosecant squared. Negative cosecant squared of unchanged 2 over x, thank you. 2 over x. There you go.
I got confused on the quiz, and I think I put x in there by accident on some questions. But
Instead of a t?
well, I mean, then
I won't count off if you put an x instead of a t, although they will on the AP exam.
I think when it's especially one where it was the derivative of cosecant, and I don't think I think I didn't put the whatever was in the print
Oh, you just put an x there?
I think I made 2 separate parentheses.
I'll have to look at it. Yeah, but this is, you got to, and look, if let's say we had y equals secant of 2x to the third, okay? Y prime, derivative of the inside is 6x squared. Derivative of the outside, what's the derivative of secant?
Wait.
Secant times tangent.
Yep, secant tangent. So, but it's secant, but it's not secant of x. It's got to be secant of 2x cubed times tangent of 2x cubed. It's anywhere you have an inside in your derivative, you have to put the inside.
Oh, I didn't do that.
Yeah. Have to.
I might have put it at the end though.
Yeah.
I think I put secant times
I think I put the
times
secant.
2x.
Not good. Yeah. This would be the correct derivative of this. You've got to put that inside. Everywhere you have an inside, you've got to put it there. Okay? All right. Let's wow, we only have 20 minutes and 15 for some of you. We've got to cover this subject. Sections 3.7, 3.8, and 3. We're only doing 3.7 today. 3.7. Now, I want you to be aware that sections 3.7, 3.8, and 3.9, we are spending exactly 1 day on each of them. So, and today's subject, it's called implicit differentiation. Implicit differentiation. Implicit differentiation. You have to be able to do implicit differentiation to be able to understand section 3.8, which we are going to do on Friday.
Yay.
Which means you have to know implicit differentiation by Friday.
Wait.
What we're doing right now, you have to know by Friday because we're going to use it in the lesson. Now, implicit differentiation. First, I'm going to write okay, so this is a function, y equals x cubed minus 7x. This is an explicitly defined function, explicit. Which means that if you give me an x value, I can give you one and one only y value. Okay? We have explicitly defined the y value as a function of an x value. Okay, we're good with that so far? I am now going to turn this explicit function into an implicit relationship. It is now an implicit relationship. Sorry. I put a square on the y. Now it is not a function. Now it is possible for any one x value to have more than one y value. Yeah. I'm about to show you. Okay, I'm about to show you.
Why do you do this? Give this man a chance to teach us.
Well, right, yeah, but I'm going to show you situations. I'm going to show you some examples, okay? All right, let's start by, I need to show you something that we've been doing for a long time. We just haven't been writing it this way. Technically, the way that you identify the derivative of a function is this, is you have to do the derivative with respect to x of each individual term, including the dependent term. So we're going to do d dx of y. We're going to do that's a terrible d. We're going to do d dx of x cubed, or sorry, I meant to put the parentheses here, okay? We're going to do d dx of 7x, and then we're going to subtract in the middle. What is the derivative of x cubed? 3x squared, right? By the power rule, right? Okay? But when we do this, something we're supposed to do, but we don't actually do, and you'll see why in a minute, is we're actually supposed to, it's a sort of chain rule thing. We actually also have to multiply it by d dx of the variable we're taking the derivative of, which is x. So dx. Okay? Right, correct. And because it's 1, we don't write it. Does that make sense? Okay? Minus, what's the derivative of 7x? 7 dx dx. Can somebody grab that? Is that my phone?
Yes.
Okay.
Nobody can grab it. Really?
Mr. Ryan? Fourth period. Class is over in about 12 minutes if he's going to be around. Okay, all right, bye. Going to have to edit this out now. Actually, I may not. I may just leave it in. Okay. Yeah. Yeah. All right, so look. Are you okay with this so far?
Yes.
All right, now, if I do the derivative of y, if we do the power rule on y, what will it be?
0. 1.
1. That's right. 1 times dy dx. We're taking the derivative of something with a term with a y in it, right? So dy dx. Now, what's 1 times dy dx? dy dx. And dx dx is 1, so we don't need it anymore. And 7 and dx dx is 1. So the answer is dy dx equals 3x squared. Can you come back in a little bit?
I gotta go. So
I'm sorry, man. How are things?
I'm great.
Yeah?
About to be in GPC with Nate, so.
Oh, good. Excellent.
Yeah.
All right, tell him I said hi.
I will.
All right, man. I'll see you later.
See ya.
Jonathan was in
Now
my
you definitely
class last
did.
year. Nah, I'll leave Jonathan in. Yeah. Okay. What's that? He went,
Voting.
oh, voting today. Okay.
18,
So he
Oh,
looked
that's
younger-
awesome.
He looked
Yeah.
younger than me,
Yeah.
but he sounded.
Yeah. He's also an Eagle Scout. An Eagle Scout. Look it up. Okay, so the derivative of this function is 3x squared minus 7x. Now, that was the long, annoying way we will never use for explicit differentiation, or excuse me, for finding the derivative of an explicit function. But now we are going to use that procedure for finding the derivative of an implicitly defined function. Does anybody recognize this?
X squared plus y squared circle.
It's a circle. It's the equation of a circle whose center is at 0 with a radius of 1. It is the unit circle.
Yes,
Okay?
to the unit circle.
Now, here's the interesting thing. Watch this. If you give me an x value, aside from 1 or negative 1, if you give me an x value, like some x value right here, how many y values are there associated with that x value? Look at it.
Less than 1.
2,
3.
3,
2. There are 2 points. This is an xy coordinate, and this is an xy coordinate, right? Both of them have the same x value. So for any one x value, I have 2 output values. So it is not a function, it is a relation. Okay? Now, if I want the slope of the graph at that point, I need the slope of the tangent line, but there are 2 points and 2 tangent lines. And those 2 slopes, are they the same or are they different? Different. So, if I wanted to know the slope of this relation where x equals, 0.5 or something, what would I also need to be able to find that answer? Well, I'm trying to find the slope. I'm inputting a number, an x value.
An x and y coordinate.
I also need a y coordinate. Because if I say x, it's going to say, well, which y do you want? Do you want this y or do you want that y? Which one do you want? Because those are different slopes. Are you with me? Which means that in the formula for slope, in addition to there being an x, there is also a y. So the derivative is actually going to have an x and a y variable in it. And I'm going to show you how you get it. Here we go. If we have this function and we want to identify dy dx, we want to identify the derivative of this so that we can find slopes at different points, we are going to use implicit differentiation. And here's how it works. The first thing, for each term, every single term, you have to apply some sort of derivative rule. In this particular case, it can be real easy. We're going to apply the power rule. So we're going to ddx this term. If we apply the power rule to this term, what do we get? 2x. And we would put dx dx, right? But we don't have to put dx dx because that equals 1. Plus, apply the power rule here. 2y dy dx. Remember everything we just did where we said when you take the derivative of something, you actually have to do d this dx. So we have to put a dy. Correct. What's that? Yes. Let me give you an example. What if I wanted to find d dt of 7a to the third power? What's the power rule here? 21a squared, and because it's not a t, I would put dA dt. You have to multiply your power rule, your derivative, by d this dt. Okay? Yeah, because it's this goes in the numerator and this goes in the denominator, okay? We're taking the derivative of a with respect to t, derivative of a with respect to t. In this case, it's the derivative of x with respect to x. In this case, it's the derivative of y with respect to x. And what is the derivative of 1? 0. And now, so step 1 is to take the derivative of each term with respect to x, then solve for dy dx.
So
How would you get dy dx all by itself here?
No, wait.
Now, I wouldn't start with division. I would not, yeah. I would start with subtracting 2x. I would eliminate or move over everything that does not have a dy dx in it. And then divide. So now we have 2y dy dx equals negative 2x. Divide by 2y. Divide by 2y. And now dy dx equals, I can cancel the 2's, right? Negative x over y. So now you give me a point. Well, on this particular function, you would one point, for example, would be 1/2 square root of 3 over 2, because it's a unit circle. Okay? So if you take the point 1/2 square root of 3 over 2, then it would be 1/2, negative 1/2 divided by the square root of 3 over 2. We can cancel the 2's. And we have negative 1 over square root of 3. That's the slope at that point. It's a downward slope. Yes, this is another way. This is the way you find a slope, the slope of implicitly defined functions. And I think we have enough time to do one homework problem before you guys leave. On page 162, question number 1 of your homework looks like this. Now you guys leave, Randy and Marquise, you leave whenever you have to, and you just watch this video when you get the chance at home. But we got just enough time to get through this question. It says x squared y, and I'm going to give you, I don't have time to really let you guys contemplate this, so contemplate it at home. Plus xy squared, plus xy squared. Does anybody notice anything already?
XY. Oh, it looks like a little
triangle.
Well, I don't know about it. It might be. I don't know this one in particular. I probably should. But I'll tell you this. We're going to have to use the product rule here and here. Because we have a product of two functions, x squared and y, and then x and y squared. So we got to use the product rule. So the first thing we got to do is we got to do the derivative of this term. We got to do the derivative of this term. Then we got to do the derivative of this term. The derivative of this term, I got to apply the power rule, or the product rule. The derivative of this, 2x, thank you, 2x, so times that, y, plus this, x squared, times the derivative of that, which is 1 dy dx, dy dx, plus product rule. Derivative of this, 1, times that, y squared, plus this, x, times the derivative of that, which is 2y dy dx.
Oh, so
Every time you do the derivative of a y, you have to slap on a dy dx.
no, but for the
Yeah.
when you find the derivative, so y and x those are the constant.
They're variables.
So why didn't you include the y? Why don't you find?
I'm doing the product rule. I'm treating these as separate functions. I'm doing the derivative of this, then times that. Yeah. Derivative of 6 is 0. And now solve for dy dx. Well, it's not too bad. We're going to subtract 2xy, subtract y squared. Right? So thank you. Subtract 2xy, subtract y squared. These cancel. And now, what we're looking at now, this is what we're now dealing with. We have x squared dy dx plus this, 2xy dy dx equals negative 2xy minus y squared. All right, you can't, I just thought about it. Yeah, if I subtract anything here, I got to subtract it over here. That's just going to make a bigger mess. Look at it. What's interesting about all of the terms on the left side? They all have a dy dx. So what can we do? Factor out a dy dx. Factor out a dy dx. So I'm going to factor out dy dx, and now on the inside is x squared plus 2xy equals negative 2xy minus y squared. One thing remains. Divide by x squared plus 2xy. This is an x, by the way. Look, we want dy dx by itself, right?
Yes.
So we have to, anytime we want to get rid of something that's being multiplied by, we divide by that. Divide by x squared plus 2xy, and that means on this side we have to divide by x squared plus 2xy, which means our final answer, dy dx, is equal to negative 2xy minus y squared over x squared plus 2xy. There we go. That's our, and leave it like this, yes.
Wait,
Where
so
do
we're
you know
just
where you
finding.
plug in dy dx? Where do you plug
Oh, we don't plug in dy dx. We get dy dx every time we do a derivative of a y term.
Oh.
If there were 7 different y terms, we would wind up with 7 dy dx's. How many y terms are up here? Or I meant to say how many terms are there that include a y? 2 of them, which means that we wound up with 2 dy dx's. Okay? I'm going to do another one real quick in blue just for anybody who watches this video and if you guys want to see it. Let's say that I did, what if I said that, oh, this is good. How about sine of y squared is equal to x squared minus y? Okay? So I'm going to do the derivative of this, which is going to require the chain rule. Okay? This is y squared. Derivative of the inside is 2y dy dx. Derivative of the outside is sine, derivative of the outside is, thank you, cosine of y squared, right? Equals power rule minus, let's make this y cubed for fun. 3y squared dy dx. Okay? Now I'm going to I'm going to add 3y squared dy dx to both sides so that I can put dy dx on the other side. 3y squared dy dx plus, now I'm going to factor out a dy dx. And I'm going to have dy dx times 3y squared plus 2y cosine of y squared equals 2x. And now all I have to do is divide by this, and I have my answer.
And then that's the slope.
And then that is the slope of this insanely crazy relation. Yeah. Yeah.
So much slope.
If you do all of the problems that I have assigned to you, I promise you, you will be just fine. You know what? If you skip the ones that you struggled with and went on and got 90% of them done, you would still probably be okay. But you have to do these problems, these practice, to be able to be good at implicit differentiation. When we get to related rates, which is the last thing we're doing this semester, all of related rates is implicit differentiation. All of related rates. But for those who know implicit differentiation, it is a piece of cake. It really is. Okay. Cake. I want cake now. Yeah.